about carbohydrates and sugars. And here we have the outline for today's class. We have definition, classification, structural examples, V and L, awards. So at the end of this video, these are words and what you need to actually be able to, boast of. But please, before we continue, if today is your first time, watching our videos, please kindly help us and hit the subscribe button. Please do it right now. Thank you. Just hit the subscribe button. All right. Thank you very much. Okay. First we said carbohydrates are naturally occurring compounds of carbon, hydrogen, and oxygen found mostly in plants and in animals. Okay. Their names usually end in O's, O-S. Right. Example: we have the glucose, the fructose, and the galactose. As we're going to be seeing now, these O's is actually not these O's, they say usually, but not all the time, because this is mostly used for monosaccharides, disaccharides. Most of the times in polysaccharides, they don't really end with O's. Just take note of that. Now, they were initially thought to have the general formula of CX, H2O, Now, that is hydrate of carbon. Hydrate means something that contains water. Initially, they thought that carbohydrate is supposed to have all of this. But you realize that as you make progress to starch and larger compounds, you realize that they don't really follow this formula. However, in case somebody asks you, can you give us a general formula of carbohydrates? You can just this can actually substitute in. Okay, now the real definitions of carbohydrates is they are polyhydroxyaldehydes or ketones or derivative of this. I'm going to explain what the definition stands for. Poly means many, right? Hydroxy means OH. So it means that carbohydrate refers to as compounds that contains many hydroxyl group, that's OH group, in addition to either an aldehyde or a ketone. Now when we proceed further, when we actually get to classifications based on functional groups, you realize that that's under monosaccharide. We're going to get to that, so let's not rush it. So take note that carbohydrates are polyhydroxyaldehydes or ketones, or the compounds derived from them. It simply means that for every carbohydrate you're going to see, the most likely going to be at least one OH. And that one OH is going to be accompanied by either an aldehyde functional group or a ketone functional group. Alright. Now, talking about classifications of carbohydrates. Carbohydrates are classified based on the number of sugar units they contain. Remember we said carbohydrate is also known as sugar. So we can classify carbohydrates based on the sugar unit, the number of sugar units they contain. As the name implies, mono. Alright? Do not forget that this guy can also be called saccharides. Alright? Sugar or carbohydrate can also be referred to as saccharide. Now, the monosaccharide refers to as carbohydrates that has only one sugar unit. Alright? They have only one sugar unit. Okay? Example of such, we have the glucose, we have the fructose, we have the galactose, right? These are compounds that have just one sugar unit. Now looking at disaccharides, di as the name implies, are carbohydrate that has two sugar units, just two sugar units. Example, we have our lactose, our sucrose, our maltose. Now we have the oligosaccharides. Now oligosaccharide refers to as monosaccharide that contains 2 carbon atoms to 8. Now it means that disaccharide can also be seen to be classified under oligosaccharide, because if something is having 2 carbons, not 2 carbons, 2 sugar units to 8 sugar units, we refer to as those kind of carbohydrates as oligosaccharides. An example of such, let's just take an example of the one that has 3 sugar units. We have raffinose. This is an example of a trisaccharide. But trisaccharide is classified under oligosaccharide. Do not forget that. Now, as the name implies here, the last one we have polysaccharides. Okay, polysaccharides are carbohydrate that contains many sugar units starting from more than 8. Remember, oligosaccharide contains 2 sugar units to 8 sugar units. This contains only 2, this contains only 1. So polysaccharide means any compound that contains more than 8 sugar units. Example, we have our starch, we have our glycogens. So that is it for polysaccharides. Okay, so we just completed our classifications of carbohydrates based on the number of sugar units. Now let's talk about monosaccharides because it's important we actually look at into details in each of them. Now monosaccharides, like you said, they are carbohydrate that contain just one sugar unit, or carbohydrate that cannot be hydrolyzed to simpler units, alright? Because since it contains just one unit, you cannot break it down further, alright? However, disaccharides and the rest can be broken down, okay? Now, let's look at monosaccharides. We can classify monosaccharides based on either their functional groups or based on the number of carbon they contain. Now, based on the functional group, we have the ones that we call the aldose, right? So any carbohydrate that is aldose means that it contains aldehyde functional group. Anyone that contains ketone functional group is called the ketose. Now, aldehyde functional group, right, has this general formula. This is a formula for aldehyde functional group, right? So, but most of the times, sometimes they can put it this way. They can put it as this. You can see they can put it like this. Sometimes. So this is aldehyde functional group. Now, example of compounds that contain the aldehyde functional group: the glucose, the galactose. Okay. Now we also have another type, which is the ketose. Ketose contains ketone functional group. All right. Now, example of ketose are the fructose. Okay. Now we're going to see this much later. Now, so in case you're in that, monosaccharides are classified into dash and dash based on their functional groups. It is based on the aldose and based on the ketose. All right. Aldose contains aldehyde functional group. Ketose contains ketone functional group. Now, based on the number of carbon atoms it contains, we can either have a triose, which means that carbohydrates, the least member of carbohydrates can contain 3 carbon atoms. Triose means 3, right? So in terms of number of carbon atoms, the one that contains 3 carbon atoms is called triose. The one that contains 4 carbon atoms is called heterose. The one that contains 5 carbon atoms is called pentose, and the one that contains 6 carbon atoms is called hexose. Right? Now, one example of I'm just going to focus on the triose and the hexose. The 2 examples we have under the triose is the glyceraldehyde, which the structure is already written there. We have the dihydroxyketone. Now, this particular one here, in as much as it contains 3 carbon atoms, this contains the aldehyde functional group, while this other one contains the ketone functional group. Alright? So, in as much as carbohydrates has different carbon atoms, they can either contain the aldehyde or they can contain the ketone functional group. So, like we said, for the triose, we have glyceraldehyde. That's the aldose part of aldose counterpart of this. And we have the hydroxyketone, ketose, this thing of triose. Now, when we come down to tetrose means 4, pentose means 5. Now, hexose is the most common or the most predominant. We have the glucose, we have the galactose, and we have the fructose. Okay? Now, glucose and galactose contains aldehyde functional group, whereas fructose contains the ketone functional group. So let's take a look at the structures. Now, this is a structure of glyceraldehyde. Now, there is an OH. Remember I said, for any compound to be called carbohydrate, polyhydroxy must contain at least one OH. This one contains OH here, and this one contains OH here. Alright, 2 OH, and this one contains OH and OH. So that definition we said polyhydroxy is satisfied. Now, this is polyhydroxyaldehyde because this functional group is aldehyde functional group. And this is polyhydroxyketone because this functional group is a ketone functional group. And do not forget that glyceraldehyde, right, is triose, contains 3 carbon that contains aldehyde functional group, which is this. Dihydroxyketone contains 3 carbon that has ketone functional group, which is this. So take note of this very, very well. Okay. Now looking down here, we have the glucose, we have the galactose, and we have the fructose. Now these 3 guys, right, they are not the only 6 carbon monosaccharide that we have, but these are the most predominant. Okay. Now if you take a look at this is the aldehyde functional group. Aldehyde, the ones that contains aldehyde functional group, their carbon is always carbon number 1. CHO, if you notice, this is aldehyde, this is aldehyde, this is aldehyde. So glucose and galactose are under the aldose, whereas fructose is actually under the ketose because of the functional group here. It is going to be OH here. It should be OH here because of this functional group. So in ketose, the carbonyl group, which is this guy, is always at carbon number 2. Whereas in aldones, the carbonyl group, which can also be written as this, is always at carbon number 1. So take note of this. For aldones, the carbonyl group is always carbon number 1, which is the aldehyde carbon. Now for ketones, the carbonyl group is always carbon number 2, which is a ketone carbon. Alright, so take a look at this. This is actually what we refer to as the glucose, the lactose. These two are aldones, aldohexose, because they are containing aldehyde functional group with 6 carbon. This guy is ketohexose because it contains 6 carbon atoms with ketone functional group. Now, having said that, I would like to explain D and L system. Now, listen class. If you notice, there is D here, there is D apart from this, because I'm going to explain that. Any sugar that you see that has D, I will explain why. If you want to know if the sugar is D or L, now listen. Look, the last carbon here. Pay attention to the last carbon. And the carbon that is directly attached to this last carbon, listen. The carbon that is always attached to the last carbon, which is this guy, will always determine if the sugar is D or L. Now, I repeat, this CH2OH, all monosaccharide, all of them must always end with this. So the carbon that is directly attached to this determines whether the sugar is going to be D or L. Now, how do we do that? On this carbon here, right, which is the penultimate carbon, if OH on this carbon is to the right, it will be D. If OH on this penultimate carbon is to the right, the sugar is going to be D. Now look at this. This guy is the OH is to the right, this is D. This OH is to the right, this is D. OH is to the right, this is D. OH is to the right, this is D. Now, the D are the most predominant in nature. Now, what if I want to get my L? Or maybe let's talk about this. Somebody may say, why is it that this one does not have D? Because this is the last carbon. The carbon before the last carbon is this guy. This does not have OH on this side, neither on this side. That is why this does not have D in front of it. Okay. Now, since you've actually understood how to get the D, what if I want to get my L? How do I get my L? Class, for me to get the L, please do not come and adjust this OH to the left. No. If you must get L, L will be the mirror image of D. How do you get the mirror image? You put a mirror. Everything on the right hand side must go to the left, right? And everything on the left comes to the right. However, what is top and what is bottom remains the same. So the mirror image of this would be this. OH was initially at the right, okay? But the mirror OH will come to the left. So once again, if you notice, this carbon here that is directly attached to this now has this OH on the left. So this is no longer going to be a D. So this is going to be L glyceraldehyde. So that is actually how we get to now our D or L. But on this carbon that is attached to this has OH to the right, that is a D. If the OH is to the left, that will be the L. And how do I get my L? I don't get my L by you don't adjust this or just this carbon alone to get your L. If you must get your L, you take the mirror image of this so that everything on the right hand side goes to the left, and that gives you the L. Now, let's take an example of L glucose. Now, this is going to be 3, 4, 5. 1, 2, 3, 4, 5. Now, look at this. The right hand side of this on the mirror will go to the left. So, this one has OH on the right, OH will now be on the left, and HB on the right. This one has H on the right, H will now be on the left. This one becomes like this one has this. So, this becomes this, and this becomes this. So this guy is now reactions of monosaccharides. Now, majorly what we intend to do today is reduction and oxidation reaction. But then, monosaccharides react with Fehling solution, Benedict solution, or Lynch reagents. Right? Now, when they react with this, they reduce these reagents. Right? When they react with this, they reduce this. These reagents are mild oxidizing agents. So whenever monosaccharides react with any one of Fehling solution, Benedict solution, or Lynch reagent, what the monosaccharide does is to reduce these reagents. As such, monosaccharides, all monosaccharides will do the same thing. Any monosaccharide will react to Fehling solution will reduce Fehling solution. Right? You react with Benedict solution, it will reduce Benedict solution. You react with Stolin's reagent, it will reduce Stolin's reagent. It therefore means that all monosaccharides are reducing sugars. So that is actually where the reducing sugars comes in play. All monosaccharides are reducing sugars. However, not all carbohydrates are reducing sugars. Remember, monosaccharide is under carbohydrate, and carbohydrates we have mono, di, poly, and the rest of them. Okay? Now, sugars that reduce this reagent are called reducing sugars. And I just said that all monosaccharides are reducing sugars. However, not all sugars will reduce this. The ones that are not able to reduce this are called non-reducing sugars. Example is a disaccharide known as sucrose. Sucrose is a non-reducing sugar because sucrose will not be able to actually reduce any one of these. Okay, now the basis upon the reduction of this is the presence of a free aldehyde or a free ketone group that is present in all monosaccharides, and it's also present in some of the disaccharides. So please take note that any sugar that reduces this are reducing agents, reducing sugars, and I said all monosaccharides are reducing sugars. The ones that are able to reduce this are called non-reducing sugars. Example is sucrose. Alright, now let's look at reductions of monosaccharides. Now, monosaccharides are reduced to alcohol. Take note of that. Alright, they are reduced to alcohols, which most of the time it is called polyalcohol, whereby some textbooks will just call it polyol. Take note of this. Now, the carbonyl group in the open chain structure, now the carbonyl group in question is either the aldehyde functional group or the ketone functional group, right? Now, in the open structure of monosaccharide can be reduced to an alcohol functional group. Now, remember, in general organic chemistry 1, right, aldehydes can be reduced, right, to alcohol, primary alcohol. Ketones can be reduced to secondary alcohol. Remember, Chem 260, right? Now, it means that if I reduce aldehyde functional group present in an aldose, I'm going to get an alcohol. If I reduce a ketone functional group present in the ketones, I'm still going to get an alcohol. So we said this carbonyl group can be reduced to an alcohol in the presence of a reducing agent, sodium chlorhydride. Okay, so we said the carbonyl group refers to the aldehyde carbon, that is carbon 1 in aldose. Remember, all aldose, the carbon 1 is actually aldehyde functional group, or the ketone functional group, the ketone carbon, which is carbon 2 in ketones. Now take a look at this example. Now this carbon you're seeing, this is carbon 1. This carbon you're seeing here contains a carbonyl group. If I'm to write it to show the carbonyl group, this is how I'm going to write it to look like. Now this is C, O, and H. Now this carbon doubly bonded to oxygen is the carbonyl group. Okay? Now reduction, when I react this with this carbonyl group is going to experience reduction reaction. And reduction reaction is addition of hydrogen in this case. One hydrogen will add to this O, and one will add to this carbon. Thereby, I'll remove this bond here, which gives rise to this. One of these H add to the O, and H add to this carbon, and I will end up removing one of the bond here. So this is actually a glucose. That's an aldose. The carbon one of this is reduced to an alcohol, which in turn, this entire structure, if this guy is now having CH2, so I can write this into the, this is CH2, so I can now write it to the CH2OH. If you look at this, there is no longer aldehyde functional group, so this is OH all through, and that is why I have earlier said it is polyalcohol, compound that contains so many alcohol functional groups. Now let's look at the fructose. Fructose is a ketone. The carbonyl group is no longer in carbon 1, it's now at carbon 2. Now the same thing is going to be done. One of this bond will go off, one hydrogen will add to the oxygen, and the other hydrogen add to the carbon, and this becomes this add to this, and this add to this, and we have this. So that becomes the reduction reactions of monosaccharides. So in case of being asked, monosaccharides are reduced to dash. They are reduced to polyol. All is a short form of alcohol, or you can just say polyalcohols, right? Most of the times, they call that those compounds alditones. Alditones, not alditones. So let's quickly talk about the oxidation reactions of monosaccharides. Now we have two major reactions here. The first one is bromine water. Now look up. In oxidation reaction, if you recall organic chemistry 1, that's Chem 260, aldehydes can be oxidized to carboxylic acid. Remember, alcohols can also be oxidized to carboxylic acid. So I want us to pay much attention. If I'm using bromine water, Alright, so I'm using bromine water, okay, to react, and then use pH of 5 to 6. This is what is going to happen. This OH group, this aldehyde functional group in carbon 1 would be oxidized to carboxylic acid. So take note of that. So what is only changing here? This is a glucose, right? Now this is glucose. Okay. Now once you react this with this, it will give us this. So this, the transformation that took place here, is actually what we have here. All right. I repeat. Now when you react bromine water at pH ranging from 5 to 6. Oxidation is going to take place, and the oxidation process is going to be conversion of the aldehyde functional group of carbon 1 to carboxylic acid. Okay? Now, let's look at the next reaction using nitric acid in the presence of heat. Okay, I'm going to come back to the name. I'll come back to the name. Let's just take a look at this. Now, this nitric acid converts the first aldehyde functional group and the last carbon to COOH. That is it. Okay? Now this is a very strong reagent. So it converts the aldehyde functional group here and the last alcohol, this entire stuff at the bottom, and the first carbon and the last carbon, if you're using 1803, it converts it to COOH. Alright? And that gives us aldaric acid. Now this, if you use only this, if you use bromine water, it converts only the carbon 1, that is the aldehyde functional group, to carboxylic acid. Okay? So how do we arrive at the name of this guy? Now since this is a glucose, glucose will give rise to gluconic acid. Now look at this, from glucose, alright? Just come here, strike out, remove the O's, and replace it with onic acid. Remove the O's and put onic acid, this becomes gluconic acid. Same thing is applicable to glucaric. Remove the O's and put aric acid to give us glucaric acid.